Hello, welcome to the Advanced Undergraduate Intermediate Graduate Series on Calculus of Variations. This is lecture CV04. It's a continuation on Euler-Lagrange equations, and in this particular lecture we're studying a class of functionals where you have many independent variables. In particular here, the functional j of u will be defined by a Lagrangian that has a spatial coordinate x in Rn, and it will depend on partial derivatives of u in each of the components of x. So let's restate that. Here is our functional definition. L is a Lagrangian. It has several arguments here. So x being space, it's Rn. You could think of this as, this actually applies to any n, but it's probably most convenient to think of this as an n is equal to 3. It could also be 4, which is relevant for doing variational principles in space-time. But so we'll just look at this. The function dependencies are important here. So L is a function of space. It's a function of u, which is a scalar function. And it depends on the partial derivatives of u in the xi's. So here I've just stated explicitly that by this gradient symbol I mean the partial of u in x1, etc. We seek to minimize j of u over a very particular kind of u. That will be u's that are C2 on this domain, which is the spatial domain here, is some subset of Rn. So it's C2 functions on the closure. And on the boundary, u is going to be some prescribed function gamma of x. When you look at this, it's very easy to decide, well, the admissible variation space must therefore be those etas that are C2 that vanish on the boundary. And why is that? Because we need to have an A star defined so that when I pick a u in A and I pick an eta in A star, this sum has to be in A. Otherwise, none of the theory works. Okay. So let's go ahead. Let's try to compute the Gateau variation of this thing. It's a little more complicated than previous examples. So the Gateau variation is I'm going to take the functional. I'm going to evaluate it at u plus epsilon eta, where epsilon is a scalar. Take the derivative of epsilon and set it equal to 0. That is what this symbol here means. So let's do that derivative without evaluating at 0 first. So I'm going to take the derivative of the functional evaluated at u plus epsilon eta. So let's look at the components of this thing. There's no change to this argument. U will be evaluated at u plus epsilon eta. And then each of the partials will be replaced by u in xk plus epsilon eta in xk. So I've highlighted the first one here as u in x1, eta in x1, etc. If I take this derivative on the outside and I take it within, it becomes a partial derivative of the integrand. So let's look at this. A partial derivative of this thing here. Well, this term here, partial derivative, will give me a partial of L and U times the derivative of the argument here in epsilon. Well, that's just eta. So that part gives me this first term. Let's take the partial derivative in the chain rule. I'll have a partial derivative in this argument here. This argument is this brown argument is the u x1 sub x1 argument. So u sub x1 is the partial of u in x1 argument. So I take the L, its partial in u sub x1, and then by the chain rule I'll pull out this extra eta in x1. And that will be the same for each of these terms. If you look at that, you can write this, you can deduce that the first variation is going to be this first term here. That'll be this term here. And then all that remains is it's a different kind of gradient of L dotted with the gradient of eta. So gradient of eta is the eta in x1 to the eta in xn. The gradient of L in the derivatives is defined to be, you take the L and you look at the arguments and the partials, and you take the derivatives in each of those partials, and that's the gradient in u prime. And so that's basically, the first component would be this, and the last component of that would be this. So here we have a compact way of writing out the first variation. So now what we do, we're going to finesse this a little bit to make it fit basically an integration by parts scheme in multivariate calc. So how do we do that? Well, we take this red term here. It's got a dot product of the gradients. We don't want to have derivatives of the etas. We want to somehow finesse things so we bring that, we do integration by parts and we bring it down the derivatives by 1, so I only have etas and not gradients of etas. So to do that, I'm going to use this product rule. This product rule, this is a scalar times a vector b, gradient of A dotted with the vector B, etc. And I'm going to identify A as being eta and B as being this new gradient of L in U prime. That, if I use these two, this A and this B in this product rule, then what I can write out that the divergence of this thing has got to equal the red term above plus this remainder term. Okay, so what I'm going to do is I'm going to take this variation and I'm going to use this last expression to replace this red thing here by this divergence minus this term here. Okay, that gives this. So then I've got the first variation of J is equal to a divergence of some expression plus a bunch of terms that multiply eta. So this is starting to look more like what we had before, Euler-Lagrange. We want to make something times eta. Okay, well, I still have to do an integration by parts. Well, how you do that in multivariate calculus is use the divergence theorem. And this is the divergence of some quantity in here. So I use the divergence theorem in Rn, and I integrate that. And what pops out there is I get the volume integral over omega is going to be a surface integral of the thing that I'm highlighting right now. In particular, this first term will become a boundary term, which is a surface integral. And I'll have the remainder term, which is a volume integral over the entire set omega. This boundary term is, by the divergence theorem, basically you take this vector field and you find its normal component. That is this here. So that's the normal component. And I integrate that over the surface. Now you notice that in this expression there's an eta here. All right? But if we go back and if you go back to what the definition of eta is, since U is prescribed in the boundary, eta must vanish on the boundary. So since an admissible variation must vanish on the boundary, that means that this entire term here vanishes on the boundary so that this entire surface integral is 0. That's great. So just look ahead. So that means that I've got this thing here is going to have this term is going to be gone then. So let's summarize that. We've got the first variation of u in the direction of eta is equal to this volume integral of an expression times eta, which is an arbitrary function in the admissible variation space. Since eta is arbitrary and continuous, and this is in the parentheses term is assumed to be continuous, we can conclude that the parentheses term must vanish. That gives us the Euler-Lagrange equation. So this thing that I've highlighted right now must vanish for an extrema by the general theory. So for this particular Lagrangian in a multivariate space, this is the Euler-Lagrange equation. Let's see how that works. I'm going to try to use this now. One slide, minimal surface area problem. This is quite dense. So we have the same setup for a surface area functional. If you know the u, and we're going to do this in R2, make it very simple. So I can picture this. So the graph of u, I'm trying to find the surface area. From multivariate calculus, if you know u of x, y, then this expression here that I'm highlighting gives the surface area of that surface over the set omega in R2. So you can imagine that picture. Maybe omega is a circle, and then above it you have a graph, and the graph has a surface area given by this formula. What you notice here is there is no explicit u's. There's only derivatives of u's in x and y. So we're going to use the same setup again. We're going to try to find out the extrema, meaning the minimum surface area of a u that has a prescribed value on the boundary. And from the general theory I just presented, whatever that u is, it must satisfy this Euler-Lagrange equation. But L sub u, this term here, is 0 because it doesn't occur in the integrand up here. So all I need to do is compute what this thing here that I'm highlighting it is. So let's take the gradient of L in the u prime argument. That's the partial of L in u sub x and partial of L in u sub y. So now you can see this what this thing here really means. It's fairly easy. So if I take the partial of L in the u sub x argument, well, u sub x occurs here. So I'm going to take the derivative of that, this whole term in the u sub x argument, and I will get this expression. Basically, it'll be something to the half. I'll lower the power, I'll get to the minus 1/2. I'll bring out a chain rule, which will be a 2u sub x in the top, and I end up with this first term here. U sub y is the same, so I get these two expressions for this gradient of L in u prime. And I just noticed that this bottom stuff here is the Lagrangian, so I can write it very simply as ux over the Lagrangian, uy over the Lagrangian. And what is the Euler-Lagrange equation for this problem? It's the divergence of that. So I have to take the divergence of this thing, the divergence of this expression right here. All right, so it's the partial in x of that first component plus the partial in y of the second component. So this is the Euler-Lagrange equation, but you can take the derivative in x and take the partial of this whole term here in x and expand it out, partial of this whole term in y and expand it out. And if you do that and simplify, this expression becomes this Euler-Lagrange, equivalent Euler-Lagrange equation in blue. And what you notice is this is a very hard partial differential equation. You cannot, there's no general theory for solving this thing. I could get some examples that would work, and the simplest one I'm just going to present here really quickly is that let's pretend that the domain of integration is the unit square. So this is the domain is going to be the unit square in R2. And I'm going to, on the boundary, I'm going to prescribe the prescribed value of u on that unit square will be whatever y is on it. And I claim that this is a formula for the extrema. Well, it certainly satisfies the boundary condition. And the question is whether or not does this thing also satisfy the Euler-Lagrange equation. Very easy to put this function into this rather messy thing here, but it's pretty clear that if I take the second derivative of that u in x twice, that's 0. The mixed partials are 0, and the second derivative in y is 0. So this function satisfies the Euler-Lagrange equations and the boundary conditions, therefore it's the extrema. We'll just move on. This last example is rather dense. So this is a slight variation of the previous problem. I'm going to do j of u is going to be defined by a Lagrangian over a volume integral plus a function g, sometimes referred to as a penalty function, that's defined on the boundary. So in other words, to find out the value of this functional, I need to know what the value of u of x is in the interior, and I also need to know its value u on the boundary. And if I know both of those things, I can compute the volume integral, add the surface integral, and that gives me a real number, which is defining the functional j of u. In this very specific case, we're going to take this L to be this thing in blue here. And why? Well, it turns out it's a very good choice. We'll see how it pans out. Everything pans out rather in an amazing fashion, actually. So I've got a Lagrangian is equal to this. It's quadratic in both u and the derivatives. And then the penalty function looks like this rather contrived thing here, which has got alphas in it, it's got gammas in it, it's got betas in it, it's got p's in it here. I got p's are over here, q's are over there, f's are over there. All of those functions, all of these functions here can be functions of x. And I'm just going to make, the only thing, my requirement on the set omega is that it's some bounded connected subset of R3, say. Could be Rn, but we'll just stick with R3. So what's going to be, this defines a very complicated functional, and we want to extremize it over some kind of set. So the set that I'm going to extremize it over are the smooth u's, basically C2 smooth, that satisfy this mixed boundary condition on the boundary. So this is an alpha, that depends on x, u plus beta times the normal derivative, this is the normal derivative, is equal to some prescribed function gamma of x. And you notice this gamma is also sitting in g up here, all right? So that's very relevant. So if I look at this admissible set, it's pretty clear that the set of admissible variations will be one where it will be smooth functions that vanish on the, that have this boundary condition vanishing on the boundary. If I do that and I take any eta out of the admissible set and I do this sum, it's in A because I've not added anything to the boundary to change that fact. Okay, so what do? At the very top here, I put, as a reminder, I put down what the function L is, the Lagrangian, and what the penalty function G is up here, all right? And I'm going to take the first variation again and do everything as I did before. It will look identical. I'll eventually have some boundary term after I've used the divergence theorem, and I'll have the same volume integral defining the Euler-Lagrange equations. But the one thing that's changed is that in this boundary term here, there is an additional term that comes from this function g. When you do the first variation, so you get this is the expression you get here. And I'll highlight, this is what we had. What we had before for the boundary was exactly what I'm highlighting now. But the addition of the extra surface integral defining j gives you this term, g sub u, in the boundary. Now, I would like to conclude that this thing is 0. I want this term to be 0. Why? Because if it is 0, then up here I get this expression I'm highlighting has to vanish, and that gives me the Euler-Lagrange equations. But I have a bit of an issue, because if eta is in the admissible variation set, that does not mean that eta vanishes on the boundary. Because I mean, eta on the boundary, it's not eta equals 0 on the boundary. It's alpha eta plus beta times the normal derivative of eta vanishes. So I can't just say, oh, it's eta's in A star, therefore this whole thing vanishes and we're done. However, even though eta does not vanish on the boundary, I can still show that this boundary term vanishes. And the reason for that is, for these very specific L's and G's, a little bit of magic happens. I want to compute this integrand here that's multiplying eta. G sub u plus the u prime gradient of L dotted n hat. G sub u, well, here's G up here. I can see this. You can see this at the very top. Here's G sub u. So G sub u is the partial of this thing in u. Just imagine taking the partial of this in u, you can do in your head. You bring down a 2 and you eliminate this u. So I get a 2u here, and I get a 1 by taking the derivative of that. So I'll have a factor of 2. I pull it out, and I get this first term here. So that's G sub u. The derivative of this thing in the partial derivative of this thing in u sub x and u sub y gives me this expression here. And therefore, this dotted n is the normal derivative of u and n. So I got a normal derivative of u and n times 2p. I got a 2 alpha p beta times this thing here. There's a common factor that I can pull out. 2p over beta times whatever in all of this. It turns out that what's left over is, okay, so I'll have, this is not supposed to be there. That is not supposed to be there. Oops. So this here, sorry, that thing right there, that's gone. I'm not going to fix it. So, but it's corrected here. So this thing does, in fact, equal 2p over beta times alpha u plus beta normal derivative minus gamma. The minus gamma comes from here. Okay, so this thing here is this thing here. But if u is in the admissible set, the thing I'm highlighting vanishes because the first two terms equals gamma on the boundary. So once again, we have that the first variation for all etas satisfies this thing vanishing because I've just shown that that's gone. What is, for this L, what is this equal to 0? Well, that's just calculations. I'm not going to dwell on it. You can compute what all this expression here turns out to be. And what it turns out to be is this first line here. It is an elliptic a self-adjoint PDE. It's a Sturm-Liouville type. And it's got a function p in there, a divergence here, plus qu is equal to f. And I've added the boundary conditions here. So those of you who are savvy with elliptic boundary value problems, this is an elliptic boundary value problem. And so what can we conclude? We conclude to minimize that j that I put at the beginning, the solution must satisfy an elliptic PDE with specific boundary conditions. That's a hard thing to do in general. And what this example actually is more illustrating is the fact that if you have an elliptic PDE problem like this and you want to solve it, one way of doing it is to go back and try to minimize this functional. So in other words, you discretize the functional and you develop a numerical scheme that would minimize that functional. And the resulting u that minimizes that j should be a solution of this elliptic PDE problem.